What are function spaces? Do the function spaces have any role in classical physics? Why should quantum mechanical function be periodic or should always vanish at the boundaries? And why should quantum mechanical operator be usually Hermitian? The answer to this setup question may help you in understanding some fundamental concepts regarding function spaces and in the application of quantum theory. In this video, I am trying to provide answer to these questions. We know from the discussion of vector spaces from the first video in this playlist that the set of all functions that are continuous on certain interval of real numbers constitute vector space. Such a vector space is called a function space or the set of real numbers. Let the function defining this vector space be expressed by small f, then a vector in this Hilbert space is written by putting the function f inside the kit notation. And the value of the function at continuous variable x is written as f of x. In the terminology of vector, this value of the function at x is called the component of vector f at position x. And the x in this case works as an index, exactly the way the index I did in the case of discrete and finite dimension spaces, where we represented the component by a sub I with index I. In other words, the vector kit f has infinite number of components over the interval, one for each value of x, where x of course varies continuously. That is, f has infinite number of components varying continuously. Now, two very important questions that should have come to your mind so far are: number first, what could be the set of orthonormal bases, because the components of vector are defined with respect to a set of orthonormal bases. Unfortunately, I will only be able to answer this question a little later in this video after I develop some background for the function space. The second question corresponds to inner product. That is, how can we define inner product on a function space? The answer to this question is very straightforward. That is, if we have two functions f and g continuous over an interval a or b in the same function space, then their inner product is written in the form of an integral over the interval as the bra of vector f times the kit of vector g time equals integral from a to b f of x times g of x times d of x. Now the function f of x and g of x are said to be orthogonal if this integral vanishes. Moreover, the function f of x is said to be normalized if the inner product of f of x with itself equals 1. That is, if the bra of f times the kit of f equals integral over a to b f of x times dx equals the integral over a over b f of x squared d of x equals 1. In other words, any function whose integral of its square is 1 is called an orthogonal function. So such set of functions constitute the set of orthonormal bases for function space over the set of real numbers x. Now, to further clarify this concept deeply, let me explain by considering this differential equation: partial square y over partial x square equals 1 over v square partial square x over partial t square. If you recall from your course on mechanical waves, this equation describes the waves over a string of length L stretched along x-axis vibrating with amplitude y along y-axis and traveling with velocity v. And further, you can recall that we can solve this equation by the method of separation of variables whose position dependent solution can be put into the form this: ym of x equals square root 2 divided by L sine m pi x divided by L, where m is a number starting from 1 going to infinity. Following Dirac notation, this equation can be written into the form ket of ym equals the rest of this equation. It can be seen that for each choice of m, we have a different function of x, where x specify a particular position along the length of the string. Now, it is not difficult to prove that the inner product for the set of these functions satisfy the condition bra of ym times ket of ym equals 2 divided by L integrated from 0 to L sine m pi x divided by L times sine n pi x divided by L times d of x, which is equal to delta sub mn, where delta is the Kronecker delta function. This means that we have m different continuous functions where each describes the dynamic of a different wave on a straight string of length L and constitute an inner product function space of infinite dimensions. That is, for each value of m, the function have infinite component where each component corresponds to a single value of x. For example, for m equal to 1, we have ket y1 equals square root 2 divided by L sine pi x divided by L, which has continuously distributed infinite component corresponding to the continuously varying value of x. So from this example, you should keep in mind that function spaces even exist in classical mechanics. However, they are spaces over the set of real numbers. So that's enough for the function spaces in classical mechanics. Let's now turn our attention to the function spaces in quantum mechanics. If the function defining the function space is complex in nature, then the definition of inner product needs to be changed. For the functions f and g, the inner product is then written as the bra of f times the ket of g equals the integral over the interval a over b f of x steric times g of x times d of x, where f steric defines the complex conjugate of function f. That is, we take complex conjugate of the function defining the bra vector. For complex function, the space becomes what is called a Hilbert space. Parallel to the scenario of classical mechanics, in this case, the set of orthonormal function is obtained from the solution of an eigenvalue equation of some Hermitian operator. That is, in this case, the hermiticity of the operator is a conditional requirement for defining the set of orthonormal bases. To see this, let me explain this through a very simple example. Consider the non-Hermitian differential operator d equal d by dx and two complex functions f of x and g of x. If these functions are continuous over an interval, then their derivatives obviously exist. That is, we can define another function as the derivative of f of x and g of x in the form capital D f of x equals df of x divided by d of x. Now let us check the hermiticity condition by using the definition of Hermitian operator for this particular operator by starting from bra of f times the ket of the derivative of g equals the bra of the derivative of f times the ket of g, which can be expressed as the complex conjugate of the inner product of the bra of g and the ket of the derivative of f, which can obviously be rewritten into this form. which in integral form can be expressed as the integral with respect to x of the complex conjugate of f of x times the derivative of g of x with respect to x equal to the complex conjugate of the integral of the complex of g of x times the derivative of f of x with respect to x. If I expand the right side by product rule of integration, I can split the right side into two components, where the first term is the product of the two functions with limits a to b minus integral from a to b of the complex conjugate of f of x times the derivative of g of x with respect to x. It is well obvious from this equation that the two sides of this equation do not agree with each other. If we carefully look at the left side of this equation, it is the inner product of bra vector f and the derivative of the ket vector g. It should obey the condition for a space to be an inner product space. That is, it should satisfy this condition. That is, the inner product of bra vector u and ket vector v should be equal to the complex conjugate of bra vector v times the ket vector u. An essential requirement for a space to be an inner product space. To validate this condition, the first term in this equation should go to 0 and the minus sign in front of second term should be a plus sign. Now it's very obvious to judge that the first term could go to 0 only if the two functions are either periodic or they vanishes at the boundaries. And the second condition is fulfilled if we use an operator of the form minus iota capital D, which can be expressed as minus iota d over dx. This operator is Hermitian. This is the reason that we always say that quantum mechanical function should either always be periodic or vanish at the boundary. And similarly, the quantum mechanical operator should always be Hermitian. Remember, for open quantum system, this condition may not be fulfilled. However, because these two conditions leads to the justification of the condition for inner product. And let me add this comment at the end that Schrodinger equation is an eigenvalue equation and the Hamiltonian describing the dynamics of the system is in fact a Hermitian operator.